Welcome to Mysterious Realms of Mathematics. I'm your host, Ted Z. Today we're going to look at Ptolemy's approximation for pi. Everyone knows the approximation 22 over 7. And many people know the approximation 355 over 113. This one is a very beautiful one, discovered some centuries after Ptolemy, and it's in a sense optimal. But few people know about the Ptolemaic approximation for pi, which is 377 over 120. I think this is a really good value for pi, and it's much more accurate than 22 over 7. And in fact, it's easier to work with because the denominator is a highly divisible number, unlike 355 over 113. For example, 2 pi is just 377 over 60. But if you're going to use the other approximation, the better one, that's 2 times 355 over 113. And things don't get simpler. They kind of get worse. Ancient astronomical measurements is, in a sense, based on the number 60. We retain some of this ancient Greek and Babylonian astronomy in our system of 360 degrees. We also have 60 minutes and 60 seconds, seconds of arc and so and minutes of arc. So it kind of would be nice to have a value of pi where the denominator is divisible by 60. Like, this doesn't cut it. This number, 355 over 113, would make Ptolemy's life a lot worse, even though in principle the computations would be more accurate. So I think 377 over 120 is a great approximation for pi. It's practical, and it's a huge improvement over 22 over 7 anyway. And this denominator makes it a lot more pleasant to work with if you're doing calculations in astronomy like Ptolemy was. So in this video, I'm going to do some theory, and then we're going to look at the question of just how good is this approximation, and we're going to do it without calculators. That's right, without a calculator. So what can we deduce from just calculus and human ingenuity with no calculators? In a previous video, I talked about Dalzell and his discovery that you can prove something about 22 over 7 and pi using calculus. Let me quickly review this idea, and if you want to see more about it, look at the video in the description box. Dalzell discovered this interesting definite integral. Why is it interesting? Well, let's look at this function here, the integrand. F of x has some interesting properties. It is continuous. I should say continuous on 0, 1. Well, because that's all we care about, 0 to 1. It is also never negative on the closed interval 0 to 1. Now, it's positive somewhere on the interior, the open interval 0 to 1. It's actually positive everywhere on the interior, but we don't need that. We just need that it's positive somewhere. So these three conditions allow us to then say that this is greater than 0. And so 22 over 7 minus pi is greater than 0. And pi is less than 22 over 7. Okay, so we did it. We proved this. It's very interesting. But the question, the mystery, here we're entering the realms of mystery. How did Dalzell discover this f of x? Now, I went through some frenzied efforts to try to figure out where this could have come from. And my conclusion is that it was an accident. So it was probably discovered by chance, and he noticed this and these conditions, and the rest is an article in a math journal, I think from 1944. I haven't read the article, so I don't know how he did it, but my guess is that it was just an accident. And so if it's just an accident, then that's sort of depressing. How can we then use this idea to prove something about Ptolemy's 377 over 120? Well, it's okay, this initial discovery here may have been an accident, but there is some theory we can deduce from this, and this is where it starts to get really interesting. And again, it's a journey into some unknown realms here. A mathematician named Backhouse noticed that Dalzell's function can be generalized in interesting ways. So here's Dalzell's original lucky function. So what Backhouse did was change these powers to make them variable. So here is the Backhouse version, and m and n are positive integers, so they're natural numbers. Backhouse called these things pancake functions. Think about it, man. What a great name for a restaurant, Backhouse Pancakes. So these pancake functions have the same properties as f of x, and this opens up a lot of possibilities for investigating integrals to try to get something interesting about pi and approximations to pi. Here are some examples of pancake functions. This one is f(5,3). Here is f(4,12). And this is f(10,2). So maybe this gives us a clue why they're called pancake functions. You notice that the bump gets really small when these powers are high and things flatten out. There's whole realms where everything is flat. So maybe that's why Backhouse called them pancake functions. All pancake functions are interesting, but Backhouse discovered some are more interesting than others. Let's take our pancake function fmn, but we'll put something specific for n here. So that's 2m plus 4k. Now this k can be any integer, positive or negative. However, 2m plus 4k has to be greater than 0 because n is greater than 0, as we said before. So this is our special pancake function, and we'll define this to be gmk, like so. Now, why is this special? Well, Backhouse proved the following. For these gmk, you can perform this polynomial division and you'll get the following results. You get some polynomial like this plus another term, which is some constant over x squared plus 1. But this is very similar to what Dalzell got for his function. So these interesting pancake functions are even more like Dalzell's function f than the other pancake functions. Okay, so why is this important? Well, we can easily integrate now. If this is true, okay, if true, then this is very good, because watch this. The integral from 0 to 1 of gmk is just the integral of these two pieces, like so. Okay, but this is easy to do. This bit here is just a rational number. And now what about this part here? Well, this is a elementary integral you learn in school. That's arctan, right? So this is a tan x evaluated from 0 to 1, and that's pi over 4. So you get this, and this is exactly what we want. This is what Dalzell got, because now we can say this is greater than 0 because this has the same properties as Dalzell's function. So this here will give us inequalities, Dalzell-like inequalities about pi and rational numbers. Great. All we need to do is to prove, let's go back up here, to prove that this division works this way, that I'll always get some polynomial, just a simple polynomial in x, and here I'll always get some constant over x squared plus 1. So let's prove that when you perform the division in gmk, you always get this form. Here is my gmk. And you notice that these powers here, this whole power is even, so I can bring a 2 inside. And when I do that, I get this. Okay, let's expand this bit inside here. All right, pretty good. So let's put some brackets here, but now I want to take that minus sign inside, watch. Like this, x squared plus 1 as one group and a minus 2x as another group over here. All right, this is a great starting point. Watch this. Let's expand a plus b by the binomial expansion. So I get this, and let's think about this. Watch, I have an a in every term here except the last one. Last one is power 0, so that's just a 1. So everything here is divisible by a. So now if I let a is x squared plus 1 and b is minus 2x, I get the inside over here, and the power p, this is my power p, like this. But everything here can be divided by this x squared plus 1, and it divides evenly. So I'll just get a polynomial. And so I can perform this division, and I'll get some polynomial here. And the last term, well, that's not divisible by x squared plus 1, not evenly. Okay, and p here, p choose p is just 1, so I get this. Now I can combine this into here because that's just more polynomial stuff. And so I get this, and let's work on this term here. Let's simplify this a little bit. So here I put the x's together. Now let's take out the minus 1. I get this, but this is an even power, so it doesn't have any effect. So I can make it a little simpler. There. Now the thing to look at here is what we have is this divided by this. The rest is just constants. Okay, so this is an even power of x, and I'm dividing it by x squared plus 1. So let's do that by polynomial division. All right, so when we divide, we get 1 and a remainder of minus 1. Let's take another even power, x power 4. When we divide, we get a polynomial up here, and then a remainder of 1. Let's do one more. Let's divide x power 6 by x squared plus 1. And we have a polynomial here and a remainder of minus 1. So if x is 2 power h, then the remainder is minus 1 power h. We see the pattern here, and you can prove this by induction, or it's kind of like a factoring problem with the infinite series. Well, not infinite series, but kind of like geometric progression, but with some alterations, you know, and you're going to get this remainder all the time. You could try to fill in the details for why that's always true. So I can look at this here and write something. And there we have it. So it's some polynomial, this polynomial here, plus this remainder minus 1 power m plus k, that's my h here, and divided by x squared plus 1. Okay, so now we've got to take this and plug that into here. And when we do that, we're going to plug in the result, okay, into here. All right, so let me show you what that looks like, doing all of that, pieces put together. We get this scary looking expression, but it's not so bad. I can combine these two. This multiplied by this is just some poly. And then what I can do is take the result of that and just add it all together here, and I get some polynomial. And there we have it. The proof is done. This is just, all of this is just a constant, and divided by x squared plus 1, and it's plus some polynomial. And this is what we set out to prove. There, I cleaned it up and I made it look nice. I just multiplied these minus 1s out. Well, our proof is done. What this means is that we can now integrate, we can choose any m and k for the g as long as It has the right condition. Remember, n was 2m plus 4k, and it has to be greater than 0. So as long as you respect this condition, you can choose any m and any k, and I'm guaranteed to get some kind of Dalzell-like result. And now let's get a result for Ptolemy's 377 over 120. But first, I want you to do an exercise. Take m is 4, k is minus 1, and show that this gk leads to Dalzell's result. In doing so, I started to wonder what will happen if I choose other values for m and k. This one turned out interesting, g5 minus 1. So I did the division, I get this big polynomial, and then this leftover term minus 8 over x squared plus 1. So I can now integrate both sides. I integrate from 0 to 1, and this here is 377 over 60, and this here is minus 2 pi. But we know that these integrals from 0 to 1 are positive, strictly positive. And so we have shown that 377 over 120 is an overestimate. It's bigger than pi. But we can do much better than this. Watch. Let's consider our g function here, g5 minus 1, on the open interval 0, 1. So we won't think of the endpoints. Okay, so if I replace x with 0, then I get a strict upper bound, like this, on this open interval. And if I replace x with 1, I get a strict lower bound. That's very interesting. Now let's plot these things. I made a nice plot. Yeah, great. So here's g5, 1. You see it's nicely bounded by those two functions. So let's integrate everything here from 0 to 1. Okay, that was easy to integrate because these are just polynomials. And I get this number, 1 over 5,544. Okay, so this is upper and lower bounds. Let's multiply everything by a half. This tells us that the difference between Ptolemy's value and pi is quite small. It's between a 10,000th or an 11,000th and a 20-something thousandth. This is an amazing result. We have a kind of a computation that shows just how good Ptolemy's estimate is. Yeah, so I rearranged things and I got pi, bounds on pi. Now, I don't even know what pi is at this point. This computation is telling me pi is in between these two. And this is quite a good bounds on pi. Watch this. Here I finally resorted. I caved into using a calculator. So it shows that pi's in between this and this here, you see. So it's quite good. And it's all done by calculus. Very amazing, truly amazing computation. Why don't you play with these pancake functions, and who knows what you might come up with. Well, that's it for this episode of Mysterious Realms of Mathematics. Like, comment, and subscribe. Send me a super thanks if you thought this was cool and if you like Ptolemy's value of pi, like I do. And I will see you next time with more fascinating mathematics stuff.